Hello, everyone. Hello, everyone. Thanks for joining for the talk. Today we have Professor Rao, who is a professor of computer science at Arizona State University. He studies fundamental problems in planning, decision making, particularly motivated in challenges of human-aware AI. Many of us know his work, and I am really amazed at some of the work his lab does, especially understanding how LRM works in the era of reasoning, planning, and decision making. Rao is also a president of Association for the Advancement of AI. He is also a fellow of ACM, American Association, AAAI, and American Association of Advancement of Science. Today is going to talk about an interesting thing of many things what we do in the lab in terms of LLM and reasoning. So he's going to give the talk on the mythos of LRM thinking tokens. Looking forward to the talk.
Thank you. Thank you. Thank you, folks. Thanks for coming. And it's always nice to be in South India where they don't ask, do you need milk and cream and sugar with coffee? I don't know what is coffee without cream and sugar, but anyway, I just had lovely coffee that Akshay got me in your cafeteria. What? Yeah, that's what I'm saying, exactly. It's the same thing. Like, essentially, you have to say, I also want chicken on the flights or something. You know, it's a vegetarian is default, yeah. But anyway, so it's lovely to be here. And I'm going to talk to you about something that's very recent work that I just actually presented. This is based on a bunch of workshop papers that we have given is this okay? Yeah, but workshop papers I've given at NeurIPS last week. I believe it's last week still. Anyway, so about the whole issue of large reasoning models and have their thinking tokens, and there is a whole bunch of mythos that has developed around it. People try to make sense of what's happening there. And it's not surprising. I assume that most of the stuff that I'm already the background you already have. So if you have questions, just raise your hand. But so obviously, these things are going to imitate the style of anything in the training data. This is a generative machine learning system. It's going to capture the distribution. It's also, and if you have training these models with traces that somehow you got in the pre-trained data, in the training data, and in fact, nobody really knows where the training data is coming from and what sort of the actual traces are there, then they will certainly produce traces that look like that. So if in fact the human produced traces said things like, aha, let me think, I will backtrack now, then the machine is going to, the LLM is actually going to say that. The question is, just because it said it doesn't mean it actually did it. And this is the issue that people think that because it said I'm backtracking, oh, it must be backtracking. So my actual joke that I've been saying is it's like having like a bodybuilding instructor, like a physical instructor for you over the phone. I'm trying to lose weight. I look at Sriram and I think, my God, I'm too broad for my good. But so then if I'm having this over the phone, that guy says like, Rao, now you're supposed to do 10 crunches. And I say, 10 crunches, done. Does that mean that I'm actually done the 10 crunches? Right? I can even say 10 crunches, and then that also still doesn't mean anything. So in general, what some model says and what actually, whether or not that corresponds to an actual action is not guaranteed. And in fact, I would argue that you should start with the prior that there is no connection, and then be surprised if there is a connection. But however, in the community right now, basically people think because it said so, it said backtracking, it must have backtracked. If it said I verify, it must have verified, etc., etc. So what we try to do is try to see whether this is actually happening. Okay. Obviously, there's standard in LLMs, and then the way I think about reasoning models that started out over and onwards. They add two things: test time scaling. Test time scaling, the way I talk about it is specifically the very simple idea of using LLM as a generator. And then if you use an LLM as a generator, it can generate many solutions, for example, or candidate solutions, or for example, it can give a candidate solution that a verifier checks to see if it is good or not. If not, you can go back and forth. Generate test is the dumbest idea in search, honestly, except unless you have a great generator. And with all their issues, LLMs are the best generators for anything in the world that we currently have. Okay, so if they are generating, they're more likely to generate stuff that's likely to be kind of true, and then the verifier will actually check whether or not it's going. That's a way of thinking of test time scaling. It works, and that actually explains why LLMs can do reasoning, because they are guessing and then somebody is checking whether the guess is correct or not. Okay, and this is not LLM verifying itself, it is an external verifier verifying it. We have called this LLM modulo, and then more recently it's become more popular as RLVR, RL with verified reward, and the verified reward comes from actual verifiers, not LLMs verifying themselves, because that's not possible. Anyway, so that's about test time scaling. And then, as Minsky said, the problem with test time scaling, of course, is it's user facing. It takes a long time. You go back and forth until you get the right thing. And one of the things is, if you want to reduce the time, if you want to increase the chance that what the generator generates is already good, so that basically you'll have fewer iterations, you can take the test time scaling, put it in the training phase itself. And in fact, that's basically what Minsky says, that the whole point of intelligence really can be thought of as taking the test part of generate test and put it in the generate part. And the more faster if the generator is actually doing things that's more close to be the correct solution, that means the probability that the verifier will actually say yes is higher, then you have improved the generator. That's basically what happens in the post-training. And one way of thinking about it is it generates huge number of synthetic data instances. Let's say if you have plans, you have lots of planning problems you generate, you have a verifier that checks if a particular solution is correct or not. And you can generate potential solutions for this in many different ways. I would basically think in terms of LLM modulo, where you generate a solution, verifiers chase whether it's good or not, and you can go back and forth. The one that actually DeepSeek R1 does is it generates 15 trajectories and hopes that one of them is correct. Okay, that verifier says one of them is correct. And it's important to understand that if you're generating 15 trajectories and if none of them are correct, you wasted that learning effort, because the problem basically is not giving you any signal. My example of this is, basically you want to prepare for the exam tomorrow. You basically take a bunch of problems of the kind that might come in the exam and prepare by basically solving them. But imagine your notion of preparation of this is look at each of the problems and saying, that's too hard, that's too hard, that's too hard. Then you are not prepared. You can say, I looked at 1,000 problems, I still did badly in the exam. That's because you didn't complete even a single problem. Now, when you do only 15 traces, the hope that if you actually have to be correct in at least one of the traces, it must be the case that you started with a very small size problems that the base model is actually good at solving. So in fact, the secret that people don't talk too loudly is that the reason RL post-training became more popular now, basically any post-training became more popular now, is because the older time, the models would not even generate a reasonable solution in the 15 guesses that they're given. They should probably have to give 10,000 guesses so that one of them will be correct. Now, over a period of time, they have come to the point that for a reasonable distribution of problems, you will at least have one or two trajectories, that will have that will be ending in the solution according to the verifier. So that gives you the signal that will lead to this improvement of the generator. And once you do this, then the actual basically once you solve the problem, if you solve enough number of problems, you can do fine tuning. The simplest fine-tuning, of course, is here's the problem, here's the solution, and then fine-tune the model. And normally we did it with SFTs before all this other stuff came along. Now, if the one trick that we basically have, that came with the post-training models is that instead of just giving problem and solution, if you give problem and something like a derivational trace, something like what people or whatever the agent doing that problem said on the way to generating the solution, that's the intermediate tokens. And if you give for each training data, basically the problem, the intermediate tokens, the solution. And if you fine-tune the model on this, as against fine-tuning the model on just the problem and solution, the accuracy is much higher. This is something that we all agree. Intermediate tokens seem to help the LLM. I'm not questioning that. The interesting question is whether these same intermediate tokens actually mean something to the end user. That's what we're trying to understand. Okay. One of the other things here basically is the SFT part. Basically, if you have intermediate tokens, you can still do SFT. There's no problem in doing it. Okay. What is RL part really? RL would have basically meant that you only look. So one of the things SFT does is basically tries to imitate the entire trajectory, if you understand how you do the last minimization. right? What you would think that RL will do is it's only looking at the outcome reward, and because it's not looking at the intermediate tokens, it might actually avoid just arbitrarily imitating the behavior patterns. It's going to optimize for the solution accuracy. Except, just a second, except DeepSeek R1's RL is really SFT. I'll say this many times, but DeepSeek R1's RL basically says, okay, here is the outcome reward, but then if you are part of the winning team, all of you get the same certificate. Every intermediate token in a winning team gets you are a winner certificate, which basically then if you're doing RL with that, it's basically SFT. The only other difference is whether you're on policy or off policy. If you do filtered iterative SFT, it's basically the same as DeepSeek R1's RL. I will mention this point, okay? It's important to understand this because all this mythos about RL generalizes, SFT memorizes, they're same, they're actually same. They're both same. And the real RL might very well be doing something else, but one that is popular, that is become a cottage industry of sorts, essentially is DeepSeek R1's RL, and it's important to understand that's what it's doing. Keep all of that in mind. Go ahead.
Terminology, right? This intermediate token, the notion of intermediate tokens is orthogonal to whether you use SFT or RL.
Exactly.
Is that how I should understand it?
Yeah,
I mean, those are different
that's
trading
true.
approaches.
That's completely true. Yeah. That is completely true. That's completely true. And so anyway, so when, in our own work, basically, before these kinds of systems came along, we showed the standard LLMs are pretty bad in planning and reasoning tasks, even though everybody was saying they're already planning, etc. And we've written lots of papers. And now they actually said, now we are really doing planning and reasoning with this reasoning model. So you must have been lying before, because if you already said it was doing planning and reasoning, why did you need another set of models? And so we actually, when O1 came along, we did this analysis and basically found that indeed it is the case that reasoning models, the O1's base performance on the same kind of things that a standard LLM like GPT-4 was doing is significantly higher. That's great, okay? But what happens, however, is as you increase actually the length of the problems, essentially the length of the plan that needs to be output, etc., the accuracy plummets, okay? And it's useful to understand why that's happening, because the idea that people tend to have is that when you are doing this post-training, the model could potentially be learning the underlying algorithm that is in the verifier, right? So in fact, first of all, I want to say that if you're doing search for anything, the first thing you need to know is if the solution comes and bites you, you should recognize it. Otherwise, how are you going to search for it? A verifier tells you whether something that just bit you is a solution or not. Okay, if you have a verifier, you invert it, you get a search. That's basically how things proceed, right? So the interesting thing is, if this verifier kinds basically giving you this feedback, one hope that people have is that maybe the LRM somehow is learning the algorithm that's, that corresponds to the planner or the verifier. What I'll tell you basically is that it's actually much more of an incrementally learning the unfoldings of the algorithm. So in the beginning, maybe it's very bad at doing, it only has top 15 accuracy of about 90% for, let's say, 3-4 step plans. Then you do post-training with either RL or SFT, you convert the top 15 90% to top 1 90% accuracy. When you do this, essentially you have increased the top 15 accuracy for the longer plans to a respectable 90. Rinse and repeat, you start doing this again. So in essentially, incremental iterative distillation is the way they learn to be more correct, quote unquote, generate correct plans or correct reasoning solutions. When you're doing post-training, and it's worthwhile understanding this. It's a very inefficient way of doing it, but since you're doing everything else is also in the same substrate, it's advantageous because the same thing can do planning, it can do reasoning, it can do various other things. So keep that in mind. The things that I want to talk about in the context of LRMs right now is what exactly is the role of these intermediate tokens? Do they have intermediate semantics, as I was saying earlier, for the end user? And also, one other mythos about intermediate tokens is the length of the mumblings is seen to be indicative of the difficulty of the problem. The more you mumble, the harder the problem is. Is that really true? In fact, one of the other things you have to understand is LLMs are obviously memory-based. Okay, so when you're mumbling more, essentially, I would actually say that the metaphor of understanding what LLMs do when given a prompt is they're trying to give a completion to the prompt given what is in the memory. So in some sense, the mumbling should be seen as them desperately trying to put together what they already have in the shelf, in trying to come up with a solution for this. And so if it's not really about the from scratch complexity of the problem, it is about how hard is it for you to fit, the solution for this with respect to what you already remember. These are very different notions of complexity. It's very worthwhile understanding that. So we'll show you that intermediate token length, for example, intermediate tokens don't really necessarily have to have any semantics, and that intermediate token length doesn't necessarily have any connection to complexity of the problem. That's what I'll show you. One other thing, of course, I'll also get into whether how does RL change any of this? And as I said, RL is not RL. For DeepSeek R1, one of the papers we presented is RL in name only. Basically, you use the word RL, but then you do this. One of the most important things RL does is takes the outcome reward and does the credit assignment as part of the learning process. Okay, you don't just say, if I have done 100 steps and then I wound up losing the game, every one of the steps is equally relevant in me losing the game. That's what RL is supposed to tell you. When you essentially said everybody gets the same certificate for being in the winning team, you completely short-circuited it. And so it's no longer really kind of the RL that it can be. It's an RL with this weird, thing that's changed. This says, go ahead.
So, hello.
Yes, go ahead.
Right. So what is the definition of reasoning that you are assuming here? Because the example that you gave was for like following particular algorithms for planning. But in the other case, when you said the LLM might have stored something in the memory and it is trying desperately to figure out what is usable from that memory, that also can be considered as a definition for reasoning.
Yeah, no, so all I am saying is they're constructing the solution guess using what is in the memory. I try not to define reasoning, just as I try not to define intelligence. It's like we can waste a lot of time, saying, but I know the examples I give, you would agree are planning and reasoning problems. And I will tell you that there is a cases where, in fact, like for example, one of the things that I'll be showing in a minute is the maze solving. Maze solving, people will consider is a reasoning problem. And I'll show you that in that context, actually, intermediate tokens don't have to have any semantics. So to the extent there is a for all understanding that basically LLMs reasoning tokens should mean something, I'm telling you that there are pretty good examples where they don't seem to mean anything. And so you should at least question your thing. Yes. Yeah.
You mentioned that intermediate tokens are really the LLMs trying to assemble what they already know.
By the way, that's a metaphor. I don't actually give as good as thing. What I show is that they don't have semantics, but I'm giving also some metaphors that you might use.
So one question I wanted is actually in a lot of work that we do, it is not just the LLM's memory, right? But also tool calls.
That's a different
Where
story.
does tool calls fit into it?
I haven't done that. Actually, we can talk a lot about this. I would be very interested in talking, but this here, it's just normal LRMs without tool calls. Tool calls sort of essentially, in some sense, allow the LLM to have experience because they're sending a call to the world and then there's something that's like an action in the world. That's a different story. I mean, I'm not presenting this as something. So anyway, so basically, we have presented these 7 papers in NeurIPS workshops, and these are all the people who did that. And advisors are nothing but, how many of you have seen Bojack Horseman? Advisors are nothing but Vincent Edelman, with their students, a big overcoat over the students. So that's what I am. I'm going to present their work to you, okay? So the thing that I'm going to talk about in terms of semantics, essentially, is intermediate token interpretability. I want to first separate 2 notions. One is interpreting how intermediate tokens seem to help the LLM. That's sort of mechanistic interpretability. That's like understanding the activation patterns, etc. I don't have a strong opinion on that. I can have a lot more discussion on that. I mean, we actually did something about it that I'll mention in the very end. But that's kind of not in the, it's not in the target right now. The one that I'm basically looking at is assuming that intermediate tokens actually mean something to the end user and that they have some connection to the complexity. That's what we wanted to check. This is like, assume. People just sort of really assume, DeepSeek R1 said that. It said, my machine said, my model said, aha. And that must mean it actually had an aha moment. Then there's a bunch of work like this tautology paper, which basically looks at the intermediate tokens, counts the number of times it said, I'm backtracking, I'm reflecting, etc., and somehow tries to make some analysis of it. There's a pretty well cited paper came out recently, which says the cognitive behaviors of a good listening model. And the cognitive behaviors, that apparently good reasoning models must say, I'm now backtracking. Like just like good fake, bodybuilders must be saying, I'm now crunching without actually doing crunching. Okay, so they did say this paper actually. So one of those questions I'm trying to do is, does any of them make sense? Okay, do any of them make sense? So the problem, of course, is how do you call the bluff? It's important to understand. It's like the point is that, well, why can't we just look at the intermediate tokens and see if in fact they have meaning? Okay, well, here is R1. By the way, first of all, let's make me point out that for most mere mortals, the only frontier model which gives intermediate tokens is DeepSeek R1. You guys have access to O3 intermediate tokens, O1 intermediate tokens, but presumably over huge NDAs saying you can't write papers on this because that's trade secret. And Gemini basically says that they, obfuscate the intermediate tokens. So most, people basically, the only place where you actually know the intermediate tokens is R1, okay? And people, when they think O1 is providing O3 is providing intermediate tokens, they're actually confusing the commentary part of the Harmony format. Harmony format has analysis, commentary, and the solution. And they're just looking at the commentary part. And there is no actual literature on how the commentary part works. It might very well have been a post facto explanation, as far as you can see. So the real question is whether, in fact, they have, whether the intermediate tokens have the thing, because all the research papers are being written on that. So here is a few block stacking problem that VC gave to DeepSeek R1. And then it starts saying the following things. These are the intermediate tokens. So my goal is to have an object C, crave an object A, the possible actions are attack, fees, succumb, etc. Looks good, looks very meaningful, right? So can you actually see whether if you do what it is saying, then it actually leads to the planet output? Well, it's painful enough if it is the first page, but that's just the first page. Second page, third page, fourth page, fifth page. 5 pages of mumblings, okay, all of which look locally like saying something. Yes, I'm now crunching, I'm crunching, I'm really lifting myself, etc., etc., with really no connection about how to actually verify whether you have done all of those things. It's impossible to verify this, okay? What people see is essentially this. You know what this is? This is Rorschach tests. Like, these are ink blot tests, and you'll say, oh, there is definitely a dragon butterfly there. Rao just drew a dragon butterfly. Rao can not draw nothing. He essentially poured some ink and then, symmetrically folded a paper, and it becomes a symmetric thing. And our cognitive flaw is to kind of make sense of every symmetric thing to have meaning. Similarly, our cognitive flaw is to make sense of every, kind of reasonable sounding English to assume that it actually has meaning, okay? So when DeepSeek R1 came, there was like a Washington Post article, and I basically told them the same thing, that essentially you should probably be thinking of these as large mumbling models because there's nobody's checking. In fact, one of the things is all the claims depend on the accuracy of the solution. None of them actually look at the intermediate tokens correctness, okay? They just say that since the accuracy is increasing, the thinking must have helped. I'm guaranteed that it's helping the LLM. The real question is it helping the humans? Okay, so actually I was one of the reviewers for the DeepSeek R1 Nature paper, and we pushed back quite significantly to reduce the anthropomorphization. They did some of it. They still had the aha moment stuff left, but they did some of that. Yes, go ahead.
But a thought experiment is that suppose you just have a filter for the thinking tokens and just delete. Will it make any difference?
Yeah, so actually it turns out that there are two different things. So we'll get to that. I'll answer your question for sure during the talk. Let me do that in a chronological way. So what I'm going to do is I basically try to convince you that if you really want to check whether intermediate tokens make any sense, you need to do a controlled experiment where the traces can be verified. 5-page mumblings for a small problem can't be verified in any which way. People are just thinking it looks like English, it must mean something, okay? So what did we do? We essentially took This is a poster that presented, this is Beyond Semantics paper. What we do is we train an empty transformer. It's a Quen 500 million parameter, or also smaller ones, but up to 500 million parameter model on bunch of mazes. And all these mazes are essentially, you generate a maze using very different kinds of distributions, Wilson-Kruskal distributions, make acyclic maze generation. These are cave generations where they essentially start removing pieces so that maze forms, etc. And there's basically, we'll try to generate these mazes into different distributions. And then for any distribution, basically you can give the maze problem instance to A star search. You all know A star search. A star search will do closed list, open list manipulations and solves the problem and gives you the actual path. So now you take the problem, the trace, and the solution. That's one instance of the training data. You do this 500,000 instances of this training data for the 500,000 things. I mean, there are many different experiments we did, but that's the kind of scale we are talking about. And then train the underlying transformer. For now with SFT, we'll do RL, quote unquote, in a bit later, okay, at SFT. And once we do this, one of the advantages is obviously when you give a new maze as a prompt in the inference stage, the model is going to first write something like an A star search trace before giving the solution. The only thing is the A star search trace can be inverted by the A star algorithm to see whether what you said actually leads to the solution that you said you got. You understand what I'm saying? So that is called the trace validity. So I actually now have trace accuracy, which I can check, and trace validity I can check too. So if that is the case, basically, and then of course, trace can be wrong in multiple ways, such as, if the most important thing is not actually producing the solution you are expecting. So we checked basically train the model with the A star search correct traces and the solutions. And then we checked in the inference stage, and basically we consider a model on, trained on Wilson traces, also both on Wilson traces and also other distributions. So you get to see both in versus out of distribution performance. And one of the things that we find essentially is as the size of the problems increases, essentially during inference stage, the trace validity becomes increasingly decorrelated with the accuracy. So as an example here, 16% of the problems it got correct solution. But of the 16% of the problems it got correct solution, only 51% actually had valid trace. The other 49% are basically saying something else that's actually not leading to the solution. This is your first thing, that they don't actually have to have strong connection. Now, if this is happening, we ask the second question, which is it actually important? Which is kind of similar to what you're saying. So one of the things I should point out here to you that in our experiments, we not only do the training with trace and the solution, but we also compare it to just problem solution. And it is well known, and everybody knows this, and we also found that the model's performance on just training on without intermediate traces is much lower than model's performance with intermediate traces. So intermediate traces help LLM. The question is not that. The question is whether it's helping humans, whether it basically are something downstream. Can you make sense of these traces? So once this decorrelation is found, we ask the second question. Does it even actually matter that the original traces were correct? I went out of my way to solve it using A star search, took A star search as correct traces, and trained the model. What if I actually went out of my way to train it with incorrect traces? There are many ways you can make traces incorrect. The one that I'm going to talk about is a swapped model. What does swapped model do? You have, let's say, trace problems P1 to P1000, and they have all correct traces and the solutions. Now I take P1's problem and P2's trace and P1's solution. That's swapped now. So I do this for every problem. So no problem has the correct trace for itself. It has somebody else's trace, okay, followed by the correct solution for its own problem. You understand what I'm saying? So if in fact this correctness of the traces seems to matter, then this should just make the model die. Not only does the model die, not only does the model not die, it does better. It does better than the model trained on only correct traces. What the heck is going on? Right? Essentially, the traces basically, so it kind of starts making it sound as if the traces are really scaffolds for the model to overfit itself to the, I'll get to you, overfit to the solution, rather than actually sort of helping the thing begin. What? All of these are basically, we are using A star verifier that's what anybody does for solution accuracy. So everybody knows to actually give accuracy claims, they're actually having a tester which checks how accurate they are. The only difference is we also can check the solution trace. Even if you are 100%, even if you're accurate, the question is, are you in fact correct trace for that? Notice that here, all the slash, basically what happens here is for the swapped model, the second numbers are all 0. Why? Because the model most of the time winds up giving traces that are like more like the swap traces rather than the correct traces. So they actually wind up being incorrect for that particular problem. They're in the right style, but they're not the correct ones. And despite the accuracy, not only is same, but it actually increases. Let me give you one more before I open the question for the question. We ask the next question, which is, what if you compare fully correct model trained with fully correct traces on one end, model trained with fully swapped traces on the other end, in between 25 swapped, 50 swapped, 75% swapped, 100% swapped. So now that basically means this is swap transformer 1, 2, 3, 4, 5. We trained 5 different transformers with 5 different data mixes, basically with the swapped and not swapped. And if you look at this, the trace validity falls monotonically most of the time. And that should not be surprising because you train with the incorrect traces. It's not obviously producing traces that would be seen to be valid by the A-star search. What's mind-blowing is this. This is actually a U curve. It's high when it's fully correct, high again when it's fully incorrect, and dies in the middle. That gives you a suggestion that what might matter is the consistency of the trace. And what the model is doing is using the trace to overfit itself to the solution signal. That at least is possible. I mean, that's basically consistent with these results. So what seems to matter, basically, this kind of questions whether in fact intermediate tokens need to have any semantics for solution accuracy. It does, at least in this case, they don't seem to. Okay, and so we presented that as a poster there. The other one, of course, is within the same thing. We can also ask whether the problem, the solution trace length is going to be connected to the problem complexity. So one simple thing that you can understand right away is we take a Wilson trace, a model generated on Wilson correct traces, and ask it to solve this slightly out of distribution problem where it just happens that there's no maze. It's just a free space. Most of you, if you know how to solve mazes, if I then give you, okay, here's the goal, there's like no chairs here, you won't say, oh my God, I didn't train for that, right? And yet the model basically dies ignoble death. It basically produces very, very long intermediate tokens and not produce the correct solution. And that's a specific telling example that you can remember. What we actually did also is we compared on the x-axis a real measure of the difficulty of the problem, which will be given by the A-star search trace length. This is just guaranteed. That's the from scratch difficulty of the maze. And then on the y-axis, the length of the intermediate tokens. If there is any correlation, you should expect some kind of a line, right? What we basically find is pretty uncorrelated because the actual problem complexity and the mumbling length are uncorrelated. There are some more interesting things. For example, if you separate these into correct versus incorrect sizes and in distribution versus out of distribution, in distribution for correct, final solutions that guesses that wound up being correct, there tends to be more of a correlation. But across everything else, basically there's no correlation. And we wound up presenting that too in efficient reasoning workshop. And apparently one of the guys asked this student Vardhan, but you guys seem to be saying something that's completely different, contradicting what everybody else is saying. If people in academia don't do that, who is going to do it? Sam Altman is never going to admit that the stuff that he's doing, works but doesn't necessarily have semantics. Okay, so I'm giving you a falsifiable, experiment, and you can undo it. Yes, sir, please.
I'm curious how you think about R10.
What?
DeepSeek R1 also.
I'll get there, that too, by the way. Yeah, but go ahead.
Yeah, so in there they showed that this English is not necessary, right? You can also train a model to generate some intermediate tokens which are gibberish, but it still gets good accuracy.
So actually, the story there is more interesting, and it actually supports everything that I'm saying, and that's I wrote it in the review. If you remember, the real contribution of DeepSeek R1 is R0, not R1. In R0, it turns out it already improves performance, but its mumbles are half English, half Chinese. And they realize that people in Silicon Valley will think that if it is in Chinese, it's not going to be good. So they just overloaded the model with SFT, extra SFT phase, so that it will only say English all the time. And it actually reduced its performance, but it got the paper into Nature. Do you understand what I'm saying? Right? So in fact, they already showed that the traces don't necessarily have to have any meaning. In fact, they can combine English and Chinese. They didn't really do that experiment, but I'm kind of showing to you that there is a possibility that it actually connects. So yes.
So in some sense, right, the hypothesis then for the results with the swapped reasoning traces is that maybe the swapped traces are just encoding in some other language.
That's possible.
And the model just makes a map.
No, it's not. Either it is the language, or more importantly, it doesn't even have to be the language. In fact, so let me give you one more metaphor. Okay, this is the metaphor of the thing. So you guys, many of you know kernel machines. The way you explain kernel machines is basically like I say that, look, you have this circular data, everything is plus inside, outside is minus. Notice you can't draw a line to separate pluses from minuses. So, but look, if you actually, blow up the dimensionality, like, look, I'll do it by saying x, y, root xy as the third axis. Now, every point there becomes a three-dimensional point here. It becomes a cone, and you can do a hyperplane that separates pluses and minuses. And then say, this is what kernel trick is. And then they do actual kernel trick. Now, if you actually think, if you know how kernel machines work, when you apply a kernel, it takes the data to some random, we don't know at all what space it takes to, and then brings it back. You don't have to provide additional semantics to which particular space it took to understand why this is working. You gave an example where there actually is meaning to the x, y, and root xy. If you use polynomial kernel, maybe it will happen. If you use some other kernel, it might not happen. But the important thing is accuracy improves. You are able to linearly separate. There are many ways in which you can linearly separate data. In particular, for example, if you go to a dimensional space where every point is a dimension, then you already trivially separate minuses and pluses. So that's the kind of thing. So I'm saying that you have to be open to the possibility that the tokens don't have to mean anything to you. They just need like a scaffold for the machine to get used to. It's basically overfit itself. One of the things that we did write about, that we did check too, for example, is in the case of correctness traces, we basically compared directly tracing, doing it on correct traces, to only taking the part of the A-star search trace that corresponds to the manipulations on the final path that leads to the solution. If you understand how A-star search does, it does a bunch of other things too. Those also are in the open closed list manipulations. But you only take the traces that finally correspond to the optimal path. It actually doesn't help. In fact, it's better. The solution to accuracy is better than no traces at all, but worse than having these much longer, A-star search traces. Now, if I was somebody else, I would write another paper on this saying optimality doesn't seem to matter. They're so smart that they can actually get by with inoptimal traces. But really, that's not there's a possibility that they don't actually care about what the trace is. As long as you're consistent, they'll basically fit it to the data. And everything else is you writing extra papers in the new RIBs, for your help. Yeah, go ahead.
So you mentioned that consistency is a factor here, but how is the swap traces consistent? Because you will not be able to assign, like there are no patterns there. It's random reassignment.
No, all I'm saying is that some are correct, some are incorrect. Again, that is a hypothesis. The path that we have shown. Any other hypothesis. So first of all, I have to say the two things. Okay. When somebody says reasoning traces have semantics and they show, look, here it said, aha. Most of us, I didn't see like people standing up on the chairs and saying, that's just one random aha. How can you say this? In general, in the field, positive, sounding results don't get questioned. negative sounding results. How do you mean? How can it not be? I'm actually showing that this actually doesn't have to be possible. And then I'm also giving you some plausible hypothesis as to why it might be. The plausible hypothesis part as to why swap trace is improving, I haven't actually tested it very clearly. But it certainly seems to be one of the plausible hypotheses as to why mix of swapped and unswapped seems to do worse than just all correct or all incorrect. Okay? Let me get, go ahead. So, I'm assuming that I can combine questions and the talk, okay? Because otherwise, go ahead.
The experiments in the previous slide, are those also over models like trained from scratch?
Yeah, they're all models trained from scratch.
And there's no like post-training or any RL?
So that's the RL right now. That's the slide. You just stopped me from doing the post-training. I'm now doing post-training in front of you. So the question, of course, is, maybe SFT actually is the problem and it's the RL that's going to save the day. In fact, one of the weird things is you have to understand that there are people who think, so I've heard people, including very respectable researchers who I shall not name, you can ask me after the talk without the mic, I'll tell you, who basically say that RL is the culprit. It essentially, in trying to just only increase the accuracy, it might be removing the meaning from the reasoning tokens. Before that, SFT actually was very nice technique, and it keeps the meaning. In fact, I'm showing that SFT already is out of the thing. And now I'll just show you that RL doesn't change anything in a minute. But before going there, I want to kind of elaborate on the RL thing that I mentioned earlier, that DeepSeek R1 RL is not really general RL. It's RL in name only. So we wrote a paper saying RL in name only, ? Analyzing the structural assumptions in RL post-training in LRMs. And the interesting point, basically, as I said already, is it has a somewhat degenerate MDP. For every RL, there is an MDP on which RL is being done. You understand that. And the degenerate MDP is the state is basically the context window, and the action is the next token in the context window. It's a weird kind of, state is basically sequence of actions, and the action is the next action. That is okay. The next part is the one that I was telling you, which is the outcome reward is equally given to everybody in the trace. That is certainly not what normal RL does. It basically is over and above what normal RL does. Now, because of that, RL tuning in DeepSeek R1 is really SFT. So I remember this slide. So you can go from SFT and you do, essentially filter. So that let the model generate its own trace. It can do that. And then reject the ones that don't get okayed by the verifier. And then do SFT on them. And then every once in a while, basically use the current model to generate. So basically, you have to have some model to generate the traces. Every once in a while, after some k iterations, you will just basically use the current model to generate the next traces. This will make it on policy. Okay, that is iterative filtered SFT. And that's basically the same as DeepSeek R1's RL. Now, if you call it SFT, people think, it's SFT. If you call it RL, wow, it's RL. But really, you have to understand what you're doing. RL can be more than what it's finally wind up doing. It can be that, but that's not what we are doing. Okay, keep that in mind. And in fact, we show in that paper that not only is it theoretically true, but in practice, doing iterative filtered SFT and doing RL, DeepSeek R1 RL, there is no difference in actual performance. So instead of writing papers like R1 generalizes, SFT memorizes, you can do this sort of thing too. This is also very relevant, and it's actually useful because you understand where the algorithms are coming from and where you might be misconstruing things. And one of the big things that we point out is because of the weird way the outcome reward is split into given to everybody in the trajectory, you wind up incentivizing RL to speak longer, produce longer traces when it thinks it's actually not going towards the solution. When it's not going to the solution. Okay, this is sort of like, some of you write exams, and when you don't know where you're going, you write longer answers. Because the hope is that the instructor would be thinking, oh my God, by 5 pages they've written, at least give half page. I'm here because I went to IIT Madras and I did physics in 1978, exactly that. I went to the physics exam and I just blanked out. What the heck is this? And basically, everybody else left. I just kept writing thinking tokens. I'm here, right? Right? So anyway, so one of the interesting things is basically DeepSeek R1 makes this claim that the average length of the think tokens increases over the epochs. And that says, look, that means the model is learning to think. What you can do is if you can separate the traces into the correct versus incorrect ones, you'll see that all the increase is really because the incorrect traces, not for the correct traces at all. What does this mean? In fact, I'll give you an idea that actually some people in AIF did, basically, which they thought of it in a very different perspective, but you will understand this perspective having what I said, which is imagine the following thing. If you are trying to generate, instead of 15 traces, you generate 1,000 traces in the post-training for each problem. Then you sort them in the length of the intermediate token traces, increasing length, and take only the top 15. This is like, you can still say I'm doing top 15, except I generated 1,000 and picked the 15 using length of length. But when you do it in terms of length, essentially you are biased to pick the ones that are going to be successful. When you are successful, you get signal from the verifier. That improves the RL's convergence. Because you can keep doing RL without getting any reward, and then basically that's not going to converge anything. So basically you spent a lot of time generating 1,000 traces and you took only 15 that are smaller, and then it is likely that more of them are likely to be ending in the correct solutions. And then I would think of this as, this is the way of doing RL such that you don't waste a problem. Like, as I said, you don't look at the problem and say, it's too hard, I won't do it. I won't do it for all the problems. Then you won't learn anything. So if you actually generated 1,000 traces, then essentially you at least got some which are going to be correct. But this paper gets written more as this is an efficiency thing. Notice that it is, in the inference stage, it is generating fewer tokens before giving the solution. And the whole point of model efficiency measured in terms of the number of tokens generated in the inference stage is a weird artifact of the fact that we are currently paying Sam Altman per token for only the inference size. That not because of any natural, profound connection between intermediate tokens produced and the complexity. So when that changes, this whole thing, we are not asking how much they spent in the training at all, for example. Okay, so that's the thing about the perspective. So these ideas for improving signal in the RL post-training, one is these 1,000 traces, the other is actually do LLM modulo or something completely to actually solve the problem so that you have a correct solution. And I've heard on the grapevine that Gemini essentially does more like an MCT style solve the problem using Gemini. MCT is kind of a better generate test than LLM modulo maybe. And then that's how basically they spend more time doing that in the training phase, but that might increase the signal they get. Okay. Now, having said that, so we presented this paper to, this is by the way, Soumya, who actually worked here. Soumya was a Akshay's RF a while back. And so, we presented that. But then the question here is, that's sort of a digression. What I really want to say is, how does RL actually change what we are talking about, intermediate token semantics? Is it improving them, for example? Okay, so we actually look at the trace validity and solution accuracy correlation over the epochs during the training. So you basically take checkpointed models and then see basically whether there's any correlation. And what we find is essentially, even for the swapped model, where there's no trace validity that ever improves, it still improves accuracy. You see what I'm saying? So it's not, what RL is basically doing is more of SFT in some sense in the way we're doing, but it's actually the case that here the accuracy is kind of increasing in a somewhat, but the validity doesn't have to increase. In some cases, it seems to increase, but in general, it's not required. It's not a for all requirement. More results there. And then we also kind of have a paper, which is probably slightly more half-baked, where we looked at GSM8K. These are all mazes. So we look at GSM8K thing and look at what the model says, like a pre-trained model says, and then try to convert that into slightly more logical form so that you can actually look at the correctness of the assertions and see what percentage of assertions are at least locally correct, not that it's globally correct. And we do see that the local correctness seems to improve a little bit more over the RL. And maybe people are misunderstanding that to mean that the reasoning is actually becoming, globally correct. Okay, that paper also was presented in the efficient reasoning. And one last thing is this all an artifact of maze problems? Maybe it's just, Rao and Rao's maze problems, maybe all the real world problems, there is actual connection. We actually did an entire parallel study, 2 more papers on just question answer scenarios. Here we took pre-trained Quen models, we fine-tuned them for these kind of, these are temporal questions, CoTemp database, including in fact the Microsoft Macro QA data set, where you can actually define a verifiable trace for them. And so you train the model with a verifiable trace, and then you check the verifiability of the traces it produces during the inference. And we basically find parallels between what we did there and what we did here. The swapped one does as well or better than the correct one. Okay, so the correlation. One other thing, so that was also presented at New Ribs. And one other thing in this particular Q&A case is when people say it's interpretable, they're saying these pieces are English. If you actually give 3 pages of stuff for humans, they'll blank out. If you give 5, they completely go comatose. If you give 10,000 pages, they basically say, I must be right. And so the question basically is, nobody really asked real humans outside of the model writers whether these things make any sense to them. We actually have IRB approval, so we did human subject studies where we trained the Quen model, we distill it using verifiable traces, which are nice and short and people actually can understand. And so when we do this study, people do say that we understand them better, and there's much less a cognitive effort in understanding them. And also distill it with R1 traces, which people basically make people go cuckoo. They say, my God, we can't make any sense out of this. Our head is hurting. And then so basically the R1 traces are cognitively much less interpretable to humans than the verifiable traces. But on the other hand, R1 traces are better at solution accuracy than the verifiable traces. These are 2 very different things. The mumblings you are doing is supposed to help the LLM. And if you want to really help the human, you should do this separately. That's basically what we are saying. So essentially, the end-user interpretability of intermediate tokens and the task performance are actually decorrelated. And you use the kind of intermediate tokens that are needed that don't have to necessarily have any semantics, and that will work for you. So that paper also was presented. So in summary, essentially, we already said this, intermediate tokens produced by LRMs don't need to or seem to have any semantics. Solution accuracy can increase even when we train the model with incorrect traces. What seems to matter is the consistency of the traces used in training. What helps the LLMs versus what helps the end user are often at odds. And then finally, RL doesn't seem to change any of this. Okay, now how does this all translate to frontier models? That's what you're here for. Who the heck cares about the little dinky model that Rao trained, right? It's like, that's true, Rao, but it still is the case that O1 and R1 know what the heck they're doing. I want to tell you that, as I said, I can't verify them, right, directly, but I want to explain to you why you might be thinking that they have reasoning, that the traces have meaning. First of all, remember that unlike our control studies, frontier models are trained on quite opaque mix of data. And they might very well have, as part of the data, first of all, traces that look saying, aha, I'll backtrack now, I'm about to reflect, etc., etc. So the real natural experiment would be to train them with the kind of non-understandable traces and see if they actually do just as well. We are not doing it right now, okay? And furthermore, the training data mix will contain some traces that are correct, probably in a weird way by humans, and some is humans just mumbling, okay? And either which way, they will produce similar stuff, similar looking stuff. In general, LLMs produce the style of everything that they see, and they'll also produce the style of the tokens that they've seen. And the other fact is that harmony format makes you realize that they're actually not necessarily showing the analysis at all. They're only showing you the commentary. And I have no idea where the commentary comes from. This could very well be post-facto rationalization. Okay, and even commentaries sometimes actually go off the rails. This is like Daniel Litt actually looking at the O3's commentary, essentially, when it's trying to solve some mathematics problem. And then suddenly in the middle, it takes a break, and in addition of, instead of math, it starts saying, let me talk about some operetta show. It seems to help, right, for the model. And you think, well, why is this doing? Because you are somehow trying to make sense of that off stuff in particular. And on the whole, there is an overall tendency to spin the same phenomenon in different ways. The phenomenon I showed you can be seen by us as intermediate tokens seem to help LRMs, but they have little end-user interpretability, and you shouldn't assume that they should. And if you are into, the other side, like Anthropic says, no, that means that the models are trying to deceive you by not telling you what they're thinking. You see what I'm saying? And I don't know why I would want to go for this, given that actually Anthropic people earlier on did an experiment which showed that ... as the intermediate tokens also improve performance. ... not even tokens. Okay? It's just, you have to understand, we are in these exciting times. Great things are happening, but skepticism is always a scientist's best friend. You see what I'm saying? So you should just ask and then, see. The other thing that I want to tell you is what might be Rao's own explanation as to what the intermediate tokens are saying. I already said scaffolding is a thing, but the way I would talk about this is that essentially prompt augmentation. So we know this much, that if you give a task prompt to LLM, it gives a completion. You can call that the probability that the completion contains a verifiable solution to the task prompt. Let's call that P1. Now I'm going to compare that P1 to the same task prompt given to the same LLM, but after the task prompt, I give an prompt augmentation, some additional tokens. There exist lots of additional intermediate sequences. All I'm saying is, does there exist one that I can add such that the completion probability, a completion containing the solution, has a higher probability? P2 is greater than P1. That is actually true. And I would argue that what the post-training is doing is learning that existential thing that you need to mumble to yourself so that you will retrieve the right thing. That is one thing. Now, if that is the case, one of the issues that you might ask is, what is the problem with anthropomorphization? Why can't you let people keep feeling good, warm and fuzzy, that LLMs actually are saying what they're thinking? My problem is they engender false belief. Let me give you an example. Suppose you have a problem. You don't know the answer to that problem at all. You give, that same problem on 2 sheets, problem description, and then 2 regions. One is scratch, one is answer. You give one to Sriram, one to Akshay. You remember, you don't know what the correct answer is. Okay, Sriram writes 7.1, and he doesn't write anything in the scratch area. Akshay writes 9.85 and writes lots and lots of integrals and differential signs, etc., in the scratch pad. Who do you think you are going to believe? I mean, of course, you're going to say Sriram is a nice guy, I should believe him. But if they're equal, then you would assume that the guy who filled up the pages must know what they're saying, which is unnecessary cognitive flaw we have, which is exactly why we know that instructors also have it. That's why we never write the answer. We keep filling pages, right? And you don't want AI systems to fight, basically like be doing an attack on our cognitive flaws. That's why I don't want to give them anthropomorphization of the tokens if in fact that's not needed. The second thing is actually more pragmatic. If the meaning doesn't matter, then you can actually tell if this prompt augmentation doesn't have to come from tokens like now I will backtrack, etc. It can come from actually, first of all, any random tokens. Most importantly, so that means they can be from different languages, but much more importantly, you all know that for LLMs, a token really is a point in the embedding space. Embedding space is dense. Some points in the embedding space correspond to words in your language. Other points don't have any words. And from linear algebra, you would say that if you assume that these words are spanning vectors, then every other word, every other point can be seen as some superposition of the existing words. So tokens are essentially these continuous latent space tokens can be thought of as like some superposition of real words, right? And they can mutter those tokens to themselves. Imagine the embedding space is a 70,000 dimensional space, As far as LLM is concerned, it's taking one to 70,000 dimensional vector followed by another 70,000 dimensional vector followed by another 70,000 dimensional vector. And it knows that the 70,000 dimensional vectors that is outputting as part of the solution better be in your language because you will get mad at it otherwise. But the intermediate tokens, if you are not looking at it, it can do whatever the heck it wants. And imagine if you are actually optimizing what is the right thing to tell yourself while taking the candidates from a much larger space versus only to a much smaller space, you would definitely can't do worse than the smaller space if you take the larger space. This is what you should see is happening in, for example, Coconut. How many of you have heard of Coconut, the continuous latent space tokens, etc.? That's basically what might be happening, essentially, So that's the way to think about it. So we actually wrote a position paper thumping the desk saying, stop anthropomorphizing intermediate tokens as reasoning and thinking traces, and we presented that too, and that's what I will end with. One last thing, since anyway, is this is mechanistic interpretability thing. This is actually not, we didn't present it, but you could be doing this whole thing not in terms of end-user interpretability, but if the activation patterns of the model seem to have some connection to the solution accuracy. So this paper that's available on arXiv, we take an algorithm, neurally compile it into a particular architecture, in this case, graph attentional neural networks. And then we also let the model learn the algorithm from the traces. And then we compare the latent activation patterns from the compiled one, that's exact, versus the learned one. And you find that they're actually uncorrelated, even though accuracy improves. So even in the case of mechanistic interpretability, there may be interesting points about this that you might be interested in. Thank you very much. That's the summary, and I'm going to stop here. Thank you.
Yes, slightly over time, but we can take 5 minutes of questions. I have to run. Surya, go ahead, and then we can take 5 minutes.
Sure. Thanks, Professor Rao. This was a great talk. This is Sunaina. We met at ACL, and I'm wondering, what your thoughts are on the state of evaluation. So I work on evals, and I feel like, in addition to your theory about the anthropomorphization, I feel like our evals are so bad that one of the reasons that we are tempted to assign meaning to these traces is because it sort of tells us that it's trying to do something versus just looking up the solution from, either it's pre-training data or it's, found the solution in some other way. So these traces sort of tell us that it's actually solving the problem versus just looking up the solution somewhere. So just curious to know what your thoughts are on the state of evals in general.
I completely agree that evaluation is a way bigger mess than anything else that I'm talking about. But I guess more people already understand that evaluations are a mess. I will say here, that Francois Chollet is one of the more reasonable people. I really like him. And then he basically came up with this RKGI benchmark. And he said, fluid intelligence is needed to solve this RKGI benchmark. And then GPT-02 or GPT 5.2 essentially saturated it. Now he says fluid intelligence has been achieved. I think it's nonsensical. Nobody ever thought that fluid intelligence means you overtrain on the RKGI database and finally hit the 98% mark. You won on that example, not necessarily on essentially, being able to look at very different kinds of problems. And to some extent, some of those benchmarks are very hard because the usual point that everybody knows is today's benchmark is tomorrow's data. In fact, today's benchmark is yesterday's data as far as OpenAI is concerned. If you remember the frontier math fiasco, they essentially paid the frontier math guys, money so that the training examples were only provided to OpenAI and nobody else. And so that they can actually do well on the test. So that's actually one of the things that happened too. So benchmark-driven thing leads to benchmarking, and we don't have much better ideas than that, but certainly we should be very skeptical. I just didn't talk too much about it because a lot more people already are worried about that direction. Anyway, yes,
Thank you.
Go ahead.
You showed that LLM may not be doing good reasoning. So
no, I didn't say anything of that kind. I'm just saying that its intermediate tokens don't have to say anything about reasoning traces or steps that you think of for like an algorithm actually going through steps and so on. It is indeed giving higher accuracy in the solutions that it's guessing. But that can be explained in terms of the generators are able to somehow fit themselves to larger and larger length solutions during the post-training.
So, okay, I mean, got it. So what is how do you think we go from here? Like how
No, we are very happy here. Honestly, there's nothing wrong with, I mean, this is the point. I'm not saying that anything is necessarily broken in the sense that LLM technology is amazing. In fact, I wish I showed this. I actually had this slide saying LLMs are an amazing 21st century reset of expert systems. And it's great because for the expert systems, somebody has to sit down and write the knowledge, and then they need to kind of use that. Now we already made the web, we wrote everything on the web, and then basically these models are actually taking our knowledge in a very different non-informal form and are able to give useful things with no guarantees. Okay, but that's a very useful thing, and it's something that we can use. You should just assume that given that basically you can ask LLMs, and in fact, this is something that Archana and Venri and we were talking about, that with LLMs, you can ask them anything. Okay, if you're trying to solve planning problems, you can ask what's the plan. You can also ask what is the planning domain for this problem. You can also ask what is the abstract strategy for solving this kind of problems. It will give an answer to every one of them, because all sorts of data is in the mix. For example, to give you an abstract strategy for a blocks world, if you put blocks in a particular configuration and get to a different configuration, what is an abstract strategy? It turns out that people in planning know that you don't need to really be in the planning, that one simple way is put everything on the table and then construct each of the stacks in the right order. If you do that, you would be within twice the optimal length, and nobody is anyway looking at the optimal length of the solutions. Okay, but this strategy, if you ask an LLM, it will give it to you very likely. Not because it actually went from the planning problem, because that knowledge also is present on the web. Essentially, it's part of the training data. Okay, so it's like a one-shot repository of all our knowledge, and then basically they can give you all this stuff, and we should just know that they will give an answer to everything, but without guarantees. And then there should be always a verifier in the loop. One of the things that I didn't show is, even with O1 and O3, if you do LLM modulo with them, but except instead of LLM, you put LRM. And that's why you let O3 guess the solution with its own post-training and all that stuff. And then the verifier still checks if it's correct or not before sending it out. And then asks it to generate another solution if it's incorrect. We actually show that improves the overall performance, but now with guarantees, because the real verifiers don't let anything go unless they're correct. Right now, all you're doing with O1 and O3 are they're better generators, so they have a higher probability of being correct. But in fact, they can still generate prompts that are actually incorrect. And in agentic systems, plans will get executed in the real world. And if in fact the actions cannot be reversed, it's an anergodic world, you can pay very huge costs. And all you need is one spectacular failure for the technology to kind of be pushed back. That's what happened, for example, for the dirigibles. I remember that Hindenburg, everybody thinks Hindenburg is a bad word, but Hindenburg, people were sitting in Hindenburg and going all the way from Germany to New Jersey. It came all the way to New Jersey, and in the last minute, it went into flames. Okay, and then that just was enough to kill that technology and restart a very different technology. So failures have very high consequences depending on your domain, and you can still put a verifier in the loop even with LRMs, because they just become, that would be a test time plus scaling plus post training together, and that is one way I would do this. Okay, so the thing that I'm avoiding answering is, how do we now reach AGI? We can have a lot of drinks after this, and I can talk to you about that, but mostly that's a useless question, honestly. Okay, it's a very useful technology. We should know how to use it rightly. Okay.
Maybe you can post the question
yeah, Twitter or anything. I'm also on Microsoft, so in fact, if there is any chat thing, you can just, I am actually kind of a Microsoft employee. I know all your secrets. So you can write anything and you can tell me anything that you're doing and I can work with you. So I'm supposedly going to be working with Ashwina, for example. So that's one of the things that, this stuff is from university. University is anyway open by definition, but the stuff you are doing, I can keep it just to myself until it comes in URIPs or iClear, if you want to talk about it. Okay. Thank you.
I mean, hi, somebody is